Thank you, Luca, for the introduction. It's so nice to be here in Padova. Really, Padova feels like home for me. And this year we had this interesting course on applied causal inference, and I hope we get some nice feedback on that. And also, in addition to Luca, thanks to Professor Turi, because we also have a Erasmus agreement between our university, Western Norway University, and Padova. So each year we get some nice visitor from Padova. So consider coming to visit us in Bergen if you are interested. A few words about the Western Norway University of Applied Science. Basically, we are a university in the western part of the Norway. The headquarters, the main campus is in Bergen, but we have campus in 4 more other cities in the western part of the Norway. And luckily, all of them are very nice places and beautiful. And we are around 20,000 students and 2,000 staff, so 22,000 the size of the university. And it's a kind of a new organization founded in 2018 by accumulation of these 5 different universities and colleges together. So the works we want to present today is a joint work with my good friends and collaborators and colleague, Professor Arghandeh in Florida State University, and also Alijan and Mahyar, his PhD students. We have a collaboration with the city of Tallahassee, the commune over there, which is the capital of the Florida. And also we got a grant from the European Space Agency to do this research. And we are so thankful for this support. So the main focus of our works is monitoring the infrastructure and understand the situation we have around the infrastructure. And when we talk about the infrastructure, we mean electricity networks, railroad, pipelines, roadways, and technically these linear infrastructures. They are where we connect, they are what connect all of us together and brings whatever we need to us. So our life depends on all this infrastructure, which is by far the largest, the most advanced, and the biggest piece of engineering that humankind built so far. However, these infrastructures, since are the most exposed elements of engineering to the weather condition, to the climate, they are unfortunately very vulnerable because in the last few decades, we were not very kind with the mother nature. So then we have this climate change, and the climate change gets back to us by impacting our infrastructure. As we see a lot of floods, landslides, and wildfire and different type of problem we see for our infrastructure. So it's very hard to keep eye on infrastructure because of the scope and the scale of this basically engineering systems. If we just want to talk about the electric grids in Europe, the length of high voltage and medium voltage line we have in Europe is enough to go to the moon for 20 times back and forth. So can we get eye on this huge infrastructure? No, it's very hard. It takes time. It needs a lot of money. Regarding the roadways we have all around the world we can go around the world or wrap the Earth 1,600 times by the amounts of highway and roads we have. So it's just imagine the scope of this problem. Conventionally, what we do, yes, we just send a guy to walk along the line, take the picture, just watch, or drive a car, or maybe a helicopter if you want to spend more money, helicopter and recently drones. Still, it's so expensive, take too much time, and it's not easy to catch up with all that data on a normal base. So satellites brings a new hope to us to look at the infrastructure from space. We can lower the costs, we can reduce inspection time, and we can increase the inspection frequency by using high quality, high resolution satellite data we have. In this study we present today, based on very nice works by Michele, we look at the pre-storm assessment and post-storm assessment. And this pre-storm assessment is good for vulnerability analysis, prevention and resilience. And the post-storm assessment basically is about the damage assessment if something's due to the extreme weather events, storm, hurricane happen. And we can also come up with some kind of recovery optimization, grid restorations, or roadway restoration, so on and so forth. So from this point, I ask Michele to continue. Thank you, Michele.
Thank you, Reza. Yeah. So here I will present some part of my research, which is the, as Reza presented, is the broad topic is infrastructure monitoring using satellites. And we are using satellite because we think it's offered the best trade-off between cost, frequency of inspection, and quality. So we don't want to say that we completely replace the conventional methods, but still satellites can offer a very useful complementary tool for this infrastructure monitoring. So we have different kind of use cases. We have power lines monitoring, and we also started another use case, which I will present here, which is mostly related to the infrastructure monitoring prior and after to the hurricanes. So when we talk about disaster or hurricane, or in general weather, extreme weather events, we can go in two different directions. So we can go, we can analyze the situation before the storm. So for example, we are interested in this vulnerability analysis or prevention and resilience to understand which type of which is the most vulnerable infrastructure for in terms of resilience and vulnerability. And on the other side, we can have post-storm assessment. So we are interested in detecting damages or recovery optimization. So basically, once the storm happens, we are interested in detecting damages. So here I will present one case study for each of these two branches that I presented. So I will first present a work that we did recently on this post-storm assessment. So basically recovery. It means that the storm already happens and we want to assess the damages and we want to see if we can detect, for example, in this case, we wanted to detect fallen trees and tree debris on roadways. And the use case is as Reza said, it's the use case in Tallahassee. It's the capital of Florida. Basically, almost every year there is a strong hurricane there. We focused on Hurricane Michael, which hit the city of Tallahassee in October 2018. So for that, we acquired high-resolution satellite images, mostly before and after the hurricane. And the reason is that we wanted to detect tree debris and fallen trees on roadways using a kind of change detection approach. So here is just as an example, we see some pictures taken from traffic cameras that we found that were pointing on some places in Tallahassee, and then at the same time also how the point looks from these very high resolution satellite images. Very high resolution images, I mean, the images we are using, they span 0.5 meters per pixel, so it's 50 centimeters per pixel, so they are very good quality. So again, our goal was to detect the fallen trees along the roadways. And we wanted to do that in a kind of unsupervised or in general weakly supervised approach. So we didn't want to train a traditional neural network to recognize fallen trees because we didn't have, in general, in remote sensing, you don't have a lot of data on that to train models in a standard approach. So that's why we developed this method, which works with very limited data. It just needs the image before and after the hurricane, and it computes the changes. So the method is it's composed of 3 different submodules that I will explain later, and then these 3 different submodules are combined together, and then will output the the location of fallen trees on the roadways. So the first method is the tree segmentation block. This is a block that we already investigated quite extensively in other use cases. For example, in another use case when we wanted to detect trees along power lines. This is based on a standard UNet. For those who are familiar with the deep learning, this is a standard UNet architecture for segmentation tasks that has been actually tailored a bit for our purposes. But the idea is that it takes you generate some patches along the roads, and then it will output the vegetation segmentation on that patch. And then these two patches are combined together, and then you compute a dissimilarity score between these two patches. In a similar way, we have another block which is called the normalized difference vegetation index, or NDVI block. So the NDVI, this vegetation index, is a very popular index, and it's calculated from some spectral bands of the satellite, because one of the advantages of using satellites is that it's not only RGB, so you don't only have red, green, and blue colors, but you have other bands that provide additional information to the scene that you might not be able to see with just normal RGB colors or RGB cameras. And one of these information is the infrared channel. And the nice thing of using this infrared channel is that vegetation looks brighter in the infrared channel, because chlorophyll is very sensitive to the infrared is very sensitive to the chlorophyll. So there is this NDVI vegetation index, which is calculated as from the red and infrared bands that can detect very effectively the amount of chlorophyll there. And again, similar to the previous block, we wanted to detect, to segment the vegetation using this deep learning architecture. Here we are computing this NDVI on the two patches, and then again, we are computing a dissimilarity score in a similar way. The idea of these dissimilarity scores is that if we have a lot of changes between the two images, that means that something changed between the two images. That's our assumption. Instead, if we have a very low dissimilarity score, it means that before and after the hurricane, the situation is mostly the same. So it's very unlikely that we will have something like a fallen tree there. And again, the third block is it's a completely unsupervised block. It's made of yeah, sorry, there is this zoom bar a bit. Okay, is implemented using a variational autoencoders. So you know that variational autoencoders is
I don't know how to get rid. What?
Okay, yeah, but then I cannot see here sometimes I think it's just yeah. I mean, I guess it's fine. Variational autoencoders is a more advanced version of a standard autoencoder. So autoencoder, you know, it's a network that tries to compress data. In this case, we are using convolutional autoencoder. So we want to compress images into a feature vector, and then it tries to reconstruct it back. And the way you train this a normal autoencoder is that you want to minimize the reconstruction error between the input and the output. So that's why the idea is that you compress the image into a tiny feature vector, which can be used to reconstruct back the image. And this will preserve the most salient information in the image. Variational autoencoder is similar, but you have another term in this loss function. So it's not only the reconstruction term of the two images, but you have another term, which is a regularization term, which is defined as a Kullback-Leibler divergence of the distribution. So sometimes it's said that variational autoencoder is a probabilistic version of the standard autoencoders. I will not go too much into the details, but the reason is that we are using this variational autoencoder is that we want to compute this dissimilarity score between the two images, again, before and after the hurricane, using this latent space. So we encode the image, each image before and after the hurricane, into this feature representation, feature vector representation. So as an example here, we are using patches of 80 by 80 pixels, and then we are encoding into just the 128 values, which is the dimension of this latent space. And then we are computing the dissimilarity score as the norm of the difference of this feature vector. And variational autoencoders we prove to work much better because since we are computing the differences in the feature vector, we wanted the latent space to have certain properties. For example, should be more continuous and smooth. And this is something that you don't achieve usually with normal autoencoders, because sometimes the feature vector are just mapped randomly in the feature space. But we want certain topological properties on the feature space. So again, yes. So here we saw that we have 3 different blocks. The input is always the same, so it's there are patches before and after the hurricanes, but then they are working in different ways and they are independent. And each of them is outputting a dissimilarity score calculated in 3 different ways. And the idea is that we can stack all the dissimilarity scores among the calculated along the entire roadways into an histogram, like a distribution function like this. And the idea is that our assumption is that if we have a very high dissimilarity score, it means that something changed between 2 patches. So it's very likely that there will be a tree debris there. And if there is a very low dissimilarity score, it means that there is not a clear change. There is not a clear change between the 2 time frames. So it's very unlikely that there will be tree debris there. The problem is that here this is completely unsupervised. So we don't have a data set that tells, okay, this is there is a tree debris or not. I mean, we will use it for validation, but for the algorithm we don't have this information. So we need to set up a threshold actually to categorize, to group this histogram, this dissimilarity scores into tree debris and no debris. So we used a method which is called maximum deviation method that try to threshold this histogram of the different dissimilarity scores into 2 families. So we say that all the dissimilarity score computed on one block, if the dissimilarity score is less than this threshold, then that patch is debris free. So basically we don't have tree debris there. Otherwise we have tree debris. And then, so this is a kind of overall pipeline of how the method works. So you have the images before and after. You run the algorithm along the roadways. Each method compute in different ways this dissimilarity score that are plotted in an histogram. You compute the threshold automatically with this maximum deviation method. And then you can combine them together because there are 3 different independent methods. So for example, you can trust more one block than another one, or you can have like a balanced combination. We tried a different combination actually. This paper is also published. So if you have some question, you can either ask me or you can also read that paper, and I provided more details in the paper. But the final output is the location of where the algorithm actually detected the tree debris along these roadways, and you can see it here on the right part. Sorry, on the right part of this pipeline. So of course, to validate the algorithm, we needed to know the location of fallen trees in the city, because it's true that the algorithm is unsupervised, so it doesn't need any training data regarding fallen trees. But in order to say, okay, that this algorithm has a certain accuracy, then we need, of course, to have a data set. So we had a data set from the municipality of Talassi that said pinpoint all the location of the tree debris and fallen trees that are stacked during after the hurricane. So here we have we can compute the standard measurement like the true positive, false positive, and false negative, depending on if we have a real tree debris and we estimated correctly or not. And then we can compute some measure like the accuracy, precision, recall, and F1 score. And then we have this table when actually we found out that the algorithm performed pretty well. So here it was one direction. So post-storm hurricanes, post-storm assessment. The hurricane happens and we want to detect some damages. There are a lot of damages that we can detect, for example, collapsed buildings or other things. But in this case, in this use case, we were interested in this in the fallen trees detection. On the other side, moving on the other direction, we can do something pre-storm. So the storm didn't happen yet, but still we can estimate the status of the grid. In this case, again, the roadway network, to see where are the most vulnerable areas prior to the hurricane. So here we come up with vulnerability formulation. So we say that vulnerability in general for an infrastructure is a combination of impact of that closure and the vegetation exposure. So the idea is that vegetation exposure vegetation is the primary cause of outages in roadways or power lines, especially after extreme weather events. So the more vegetation we have, or the more high, or the more exposed is the infrastructure to the vegetation, the more likely it is that we have an outage there. But then we also have to consider the impact, which takes into account the effect of the outages on the network. For example, let's consider if we have a road with a lot of trees, surrounded by a lot of trees, so the vegetation exposure can be high. But then if nobody is using that road, it's not very important for the overall mobility or in terms of transportation network, then the vulnerability can be lower. So here we have these two different terms. So we have the vulnerability, and then we have the vegetation exposure, which is calculated based on some 3 parameters that we can estimate from satellites. And then we have the impact. So as consequences of a roadway closure, we take into account the building density and the road importance. And I will go through it through this each term in the next slides. So for the vegetation exposure, we tried to estimate some 3 parameters directly from satellite images. So we are computing a vegetation exposure, taking into account the number of trees along the road, their density, their distance to the center of the road, and then their height and their health. And then a posteriori, we try to correlate the vegetation exposure that we calculated with the location of the tree debris that we have. We found out that actually most of the roads where we had actually a posteriori, so after the hurricane, tree debris, it also had a very high vegetation exposure. So for the vegetation exposure, we first estimate the height from satellite images. So this is a very tricky point, because it's very hard to estimate like a 3D dimension from a satellite images, because you are just looking on top, so you don't really have you can measure the height, but you can try. Actually, we try to regress the height using again with a deep neural network. So again, this is similar to the segmentation model that I showed before. Actually, this is a rescue net. that has been trained to regress, to map the contextual information that we have from satellite images into a 3D value to try to generate a surface like this digital surface model of the area. For the vegetation health, we used again this normalized different vegetation index, and we compute these NDVI from multi-temporal images that we acquired over the year, and then we compute the mean over the year, and then we compute this delta on the NDVI. The reason here is that NDVI is related to the amount of chlorophyll that we have. So if we have a positive trend on this NDVI over the years, it means that there has been growth in the trees. If it's close to zero, it means that probably more or less the trees have been stable over the years. But most importantly, if we have a negative trend, then it means that we have a decay on the nature of the tree, which can be caused by parasites or illnesses, or in general different factors. But the important thing is that decayed trees is more vulnerable to, it's more unstable as a physical structure. So there are of course some filterings here, because it's you have some different changes in the NDVI, natural changes given to the phenological cycles of the plants. So plants in general have different values of NDVI depending on the season and depending on the different meteorological factors. So you have to filter a bit. But what you are interested in is actually the overall trend. And then again, here we can put everything together into this vegetation exposure. So we have the height. From the height, we can estimate the presence of the trees using some local maximum filtering, for example, and then we can estimate the distance from the trees to the road, their health, and the number of trees, and then we can put everything together and calculate the vegetation exposure over the road. And then we have the other thing. We have the other term, which is the impact of a closure. So we have the road importance and the amount of building. For the road importance, we are interested. We are working with the roadway network. So we calculated the road importance. Yeah, sorry, here as we first turned the roadway network that we have into a graph, the corresponding graph. So edges, the nodes of this graph means they are the intersection between roads, and the edges of this graph are just the roads. And so we can turn this, again, there is some pre-processing here, but you turn the roadway network into a graph, and then you can run some graph analysis algorithm to estimate which edges are more important than others based on the topology of the graph. So in this case, there are a lot of measures that one can think of, but we use the edge between a centrality, which is calculated using this formula. So it just is calculated based on the ratio of all the given two nodes in the graph. It is calculated as the number of all the shortest paths that are passing through the edge, divided by all the shortest paths on that between two nodes. So the idea is that if we have in an edge, we have a lot of shortest paths that are passing through that edge, it means that that edge is very important. And so we can assign a higher value to that edge compared to another edge with less between a centrality, because it means that if we have a closure there, it means that we cut that edge in the graph, and then it will affect more the transportation compared to other edges that are less important. And then we have again the buildings. So we use the buildings as a kind of proxy for the amount of citizens affected by outage. So in the first, initially we were using the satellites to estimate the building footprints from the images automatically using again segmentation tasks. But then we realized that most of the cities actually have already some data set that shows the building footprints and also their height, and everybody can download it for free, these kind of images. So, and we realized that even though it's possible to use satellites to estimate the building footprint, we thought that probably it's not really worth it, because you can directly estimate it. You can already retrieve all this data accurately from for free from OpenStreetMap, for example, which is not the case for vegetation. So for vegetation, usually you don't have extensive data set about this, but for buildings or roads, usually you have. So that's why we are not using satellite images to estimate the building footprint, but we are using a data set from this OpenStreetMap.
So if there are somewhere in the world they don't have such a data set, it's possible to extract the buildings information from the satellite image directly, or roadways from the satellite image, or the pathway for the power line. All of them is possible.
So the idea is that here you can combine everything together. So you just use you use the information from the municipality, for example, the roadway location and the building data set. You calculate the building density, and you run this topological analysis on the roadways, and this gives the impact. And then the main contribution is basically from the satellites. So roadways and buildings doesn't change too much from one year to the other, and the data set are always updated from the municipality. But for the vegetation, actually you can have up-to-date information from the satellite images using this kind of algorithms. So you can estimate this height estimation. You can estimate the height. You can estimate the health. You can and then you can compute this vegetation exposure, and then you plug everything together into a vulnerability map that takes into account both the vegetation, both the kind of likelihood or the vegetation exposure of this on the roads, and also the impact of this closure on the transportation networks. So yeah, these are some kind of some publication that are already out there based on this on some works that we did. There are more that are still under review, so it's hopefully I will add more items to this list. And then I finished.
Thank you. So
I hope it will be